we'll talk about some logical equivalences. So first, a compound proposition is called a tautology if the proposition is always true, regardless of the truth values of the individual propositions. So this is something that if we build a truth table, the final column would just be all true. A contradiction is going to be the opposite of that. This is a compound proposition that is always false, regardless of the truth values of the individual propositions. So for example, P or not P is a tautology, since this is always true. If P is true, then we have a true or false, which is true. If P is false, we have a false or true, which is still true. P and not P is a contradiction. If P is true, we have true and false, which is false. And if P is false, we have false and true, which is still false. To show something's either a tautology or a contradiction, you should construct a truth table. And showing that every row in the final column is a T gives a tautology, and showing that every row in the final column is an F will give us a contradiction. If there's some combination of true and false, it's neither a tautology nor a contradiction. So here's our examples from earlier. If I have P or not P, my final column is all true. And if I have P and not P, my final column is all false. We say two propositions are logically equivalent if they have the same truth value, regardless of their individual propositions. So if S and R are two compound propositions, we use this notation of this triple equal sign, which is just an equivalent sign. And this indicates that R and S are logically equivalent. So for this, we should have the same truth values. So I should be able to build the truth table for each of them, and the final column should be identical. So for example, P and a double negation P have the same truth value, regardless of whether P is true or false. So P is equivalent to the double negation of P. And propositions S and R are logically equivalent if and only if the proposition S, if and only if R, is a tautology. And we can use a truth table to show this. Like I said before, we just need the final columns of each of the propositions to look identical. So let's show this one. Not P or not Q is equivalent to not P and Q. So we start with the columns for P and the columns for Q. The first thing I'm going to do is do the left-hand side, which has a not P. So this changes all the trues to false and all the falses to true. Not Q will do the same thing. Change T to F and F to T. Then we have the negation of P or the negation of Q. So this is an or statement between the negation of P column and the negation of R column. So the first one we have false, false, which would be false. And the rest will be true, since at least one of them is true. On the right-hand side of this, we'll first deal with what's in parentheses, the P and Q. For P and Q to be true, we need both P and Q to be true. This only happens in the first row. And then we need the negation of this, so we'll change all the T's to F's and all the F's to T's. And we can see that these two columns, one that belongs to the left-hand side and the one that belongs to the right-hand side, are identical.